Quiz 1, Spring 2010. Problem number 2. Timothy Leary's calendar app. In this problem, the dwindling population of a 60s-era cult is trying to rejuvenate their membership via an iPhone calendar application that emphasizes the cult's peculiar values. You've been asked to help by coming up with an encoding that conveys one of the following tidbits about today's date. The code transmitted to a user's iPhone is specified by the first of the following 6 descriptions that applies to today's date. So right away, we know that there's 6 possible messages. So we want to make note of that. So, there's various messages of today's an equinox, birthday of one of the cult's 3 saints, Thelonious Monk, Victor Hugo, Tiny Tim, first of a new season, etc. So we can revisit that. We want to look at problem A, which is, what is the number of bits required to encode each of the above 6 messages in a fixed length code for each of the following cases? So the closest power of 2 that's still bigger than 6 is 2 to the 3rd, which is 8. So we would need at least 3 bits without any kind of error detection or correction. In order to have single bit error detection, not worrying about correction, we need to increase the Hamming distance by 1. So we would all of a sudden have 2 to the 4th, or up to 16 possible different encodings for our messages. So that's 4 bits. Now, we're going to talk about what we get when we have a variable length encoding. So in problem B, we're going to devise a variable length Huffman code that encodes the above 6 messages with the minimum average message size, so that with no error correction or detection. So we want to know the number of bits used to encode each of the above messages. So we want to talk about, so A, if today's an equinox, there's 2 of these per year. So the probability of A, we're going to do our probabilities. The probability of A is 2 out of 365. Right? Now what's B? If today is the birthday, so there's 3 birthdays of a cult saint per year, so it's 3 out of 365. C. If today is the first day of a new season, there are 4 of these per year, so 4 out of 365. D is if today is the first day of the month whose name does not end in R, so it tells us there are 4 of these per year, so we know that's also 4 out of 365. E. If today's a weekend, other than above special cases, there are about 100 of these per year. So we'll say 100 out of 365. And then we have F, which is otherwise. So 2 plus 3 is 5, plus 4 is 9, plus another 4 is 13. So all these would be 3 out of 365. So that leaves us with, what's 360? Sorry. So 365 minus 113 is 252. So that gives us 252 out of 365. Alright, so in order to do a variable length Huffman encoding, we know that we always want to start with the 2 nodes that have the smallest probability. So just using a slightly different brush color here, we can see that A and B have the smallest probability. So we'll cross them out, A and B, and we'll make a new node, right, called AB. And the probability is 2 plus 3 equals 5 over 365. So we can do A, B, right, and this is AB in our Huffman tree that we've started to draw. Now we're going to find the next 2 with the smallest probability. So we have C and D. So our new node could be CD, and that's 8, right? 4 plus 4 is 8 out of 365. So we'll draw C, D. Okay, and that's CD. Okay, so next 2 smallest are still A, B, and CD. So 5 plus 8 it's going to give us A, B, C, D. 5 plus 8 is 13 out of 365. So A, B, and C, D come together to make A, B, C, D. Now the next 2 smallest, we have our 13 and 100, so that'll give us A, B, C, D, E, right? So we have A, B, C, D, and E gives us, and that's 113 out of 365, right? So that's A, B, C, D, E. And finally, A, B, C, D, E, and F should come together to make a probability of 1, right? Because F's the final one. So now we have our Huffman tree. So we can go back and we can determine the number of bits for each of these cases, right? So the number of bits for message number A, we go 1, 2, 3, 4. Alright, so number of bits for A is 4. Number of bits for message B, 1, 2, 3, 4. Number of bits for message C, 1, 2, 3, 4. Number of bits for message D, 1, 2, 3, 4. Number of bits for message E, 1, 2. Number of bits for message F, 1. And now we're done.